We're finally starting a new unit today, dealing with thermal physics. I tried to give you as many of the notes already in your packet so that you can follow along, listen to what I'm saying, and fill in. Not as much, because really there's no point in me writing everything down here. But what you have there, the very first thing that we want to define is internal energy. Okay? And internal energy, you're going to want to use the symbol U for this. Alright? And it will be measured, it's a capital U, and it's going to be measured in joules, of course. All the energy that we'll be dealing with will be joules or kilowatt hours once we get to that. But the idea of internal energy is this combination of all the possible potential and kinetic energy that a substance can have between its constituent molecules. Alright? So internal kinetic energy, alright, we often think of this just as thermal energy. It's often exchanged like this, but it arises from all the different possible motions we have of molecules. So what we can see with molecules is we can see a translational type of motion, we can see a rotational type of motion, and we can also see a vibrational type of motion. Okay, vibrational gets at the unit we just studied with simple harmonic motion, the mass of a spring oscillating. Rotational gets at these ideas of torques and angular momentum, stuff we have not studied, nor will we. And translational, think of everything we've done with kinematics, okay? So that is our three different types of kinetic energies that we can have. And when you think of thermal energy that a body possesses, this is the way you're typically going to think of it, okay, is the motion of the particles, okay? That's what heat is, effectively, all right? Heat isn't a substance, okay? It's just how way we quantify the motion of particles. How particles are arranged, okay, whatever kind of crystalline structure that they may have, the interaction between their electrons is going to give rise to these intermolecular forces, and basically how close they are, you can think of is how much potential energy, internal potential energy, that substance has. Okay, so really, their desire to really just knock each other apart with all those outside electrons, but really, they're satisfying those electron states so they stay together. But there's still that stored potential energy there between them. Okay, so those are three big ideas right there that you need to be aware of. So let's start out with temperature. All right, the first way we think of temperature is that it is a measure of the average kinetic energy of all particles of a system. Okay, so we defined it with a big capital T. It's units. We have Celsius, Kelvin. In the English side we got Fahrenheit and Rankine, the analogs to Celsius and Kelvin, but we will not be dealing with those. All right. Dealing with Celsius and Kelvin, the conversion that you need to be aware of, that I'm sure you've learned in chemistry. So a lot of this unit you'll see is going to be a repeat of what we've done in chemistry. Nothing really, what you've done in chemistry in terms of specific heat, MCAT, I think is one equation that's really going to pop in your head. So when we look at the average kinetic energy of molecules, what we're talking about is that a bigger molecule may have the same kinetic energy of a smaller molecule if that small molecule is moving faster, right? So we're talking about all the net, different molecules, their average kinetic energy. That gives us an index of what the temperature is. And if we look at that temperature on a Kelvin scale, this is the graph that we get between the two of these. It is directly proportional. Now, if we look at this with Celsius, all right, what ends up happening is it ends up being shifted over, okay? And what we see here at 0 Celsius is actually at 251 Kelvin there, okay? Actually, no, excuse me, I take that back. 273 Kelvin, sorry. So anyways, yes, that is the idea there. And the difference in these slopes, actually there shouldn't be a difference in these slopes, so we'll redraw this there. That's a little bit better, all right? Okay, so that's our first definition of temperature, is just, an index for us, all right, to see how fast things are moving. If you want to see the derivation for this, it's pretty cool, but the Giancola textbook I have in the classroom has that, and it actually gets into statistical distributions there. So, yeah, you can check that out anywhere online as well. The second definition, though, okay, deals with thermal energy, all right? So thermal energy is what we think of as energy that's been transferred between two substances by non-mechanical means. In other words, we're not, necessarily actually doing work, okay? It's just the flow of energy. And the way that this can happen, there's three different modes of heat transfer: conduction, convection, radiation. Hopefully you remember those from 8th grade physical science. If you don't, that's okay. Conduction is the movement of heat without bulk transfer of medium. Convection is the movement of heat with bulk transfer of medium, and radiation is just electromagnetic radiation. So the symbol for thermal energy is going to be Q. And of course its units are going to be in joules. All right? Nothing new there. Capital Q, and sometimes it's a delta Q there that we think of because we're looking at the change between substances. So if we see here, okay, we have two blocks. One's at 100 degrees Celsius and another 0 degrees Celsius, both made of identical materials, okay? And we want to know, okay, which way is heat going to flow between these substances? First of all, okay, I want you to think about this. Which one is the hot one, which one is the cold one, okay? You would obviously say the one with the higher temperature is the hot one, the one with the lower temperature is the cold one. Well, I want you to get rid of these notions of hot and cold, okay, as you already have them. The reason is there is no such thing as cold. Everything is heat or lack of heat, okay? So what we have here, right, is temperature, which gives us an idea, an index of how much heat, okay, that substance has, all right, gives us an idea. It gives us the average kinetic energy of molecules. We know that kinetic energy is related to the amount of heat a substance has, all right? And what we see here is that we know the heat is going to flow from where there's more of it to where there's less of it. Okay? In other words, temperature actually tells us the direction of thermal energy transfer between two objects. And that's your second definition on your page right there. Okay? So when we're finished here, both are going to have the same temperature, whatever temperature that is, X degrees Celsius, and this is what we call thermal equilibrium. Okay? So with thermal equilibrium, okay, two objects, all right, objects are at the same temperature, and what we have is no thermal energy transfer going on between them. Okay? All right, so those are your two big ideas right there, thermal equilibrium and what thermal energy is, okay? And that gives us the second definition of temperature. So a few definitions before we go on here. What you need to know are thermal capacity, and this is also known as just heat capacity, and specific heat capacity, all right? So thermal capacity is going to be the amount of energy required to raise the temperature of the substance by 1 degree Kelvin, 1 degree Celsius. Okay? Oh, this gets at another interesting point. Go back to the temperature piece right here, really quickly. Okay? With this temperature thing here, if we take this equation, right, and look at this, if the temperature in Celsius goes up by 1 degree, how much does temperature in Kelvin go up? 1 degree. Temperature in Celsius goes up by 2. How much does Kelvin go up? By 2. Okay? What we see here is that the change in Kelvin is equal to the change in temperature in Celsius. All right? So anytime I talk about an increase in temperature in Celsius, it is interchangeable with using the unit Kelvin. Alright. So, thermal capacity, we raise the temperature of a substance by 1 degrees Kelvin. That's the overall amount of energy required for that single object. Okay? The difference here, specific heat capacity, gets at this idea that it's not just the amount of heat needed per degree Kelvin, but amount of thermal energy, heat needed, okay, to raise the temp by 1 degree Kelvin per kilogram, per 1 kilogram of substance, okay? So, if we look at formulas here, right, thermal capacity is big C, and it's equal to delta Q all over delta T, all right? The symbol, like I said, is big C, okay, and the units, you could probably guess, are joules per Kelvin. All right? For specific heat capacity, it's little c, and what we're going to call it is delta Q all over m times delta T. And this is where our MCAT equation comes from. Okay? So the units here are going to be a little bit different. but you're going to see them as joules per Kelvin per kilogram, or sometimes they're written joules per kilogram per Kelvin. All right, and that's it. Okay, those are two equations of the three that you'll be getting this chapter. All right. So if we take a look at a quick example, we have two blocks, all right, made of the same substance, but one has more mass than the other. So the question is, why do different amounts of the same substances have different thermal capacities? Well, what we have here is more molecules to store that heat that's been transferred into it, or that internal energy. Okay, so that's why more mass will be able to hold more heat. Okay, there's more molecules to vibrate and store that. The next one, though, why do the same amounts of different substances have different heat capacities? Well, again, this deals with the fact that substances contain different numbers of molecules with different molecule masses. Hopefully that's getting at this idea of the mole. You remember from chemistry, okay? You know, you can have a kilogram of lead and a kilogram of hydrogen, but you're going to have a lot more hydrogen atoms in that kilogram than you will of the kilogram of lead, because single atom of hydrogen, you know, has so much less mass. So it also deals with, you know, the structure of the substance. There's many different things there, but the main idea there is getting at this idea of moles. Okay, so let's do a practice calculation here. We have some sample of lead. We're given the heat capacity of the sample, okay, and we're told that what is the thermal energy released if it cools from 61 to 25 degrees Celsius. So we see here we have a change in temperature of negative 36 degrees Celsius, and we're asked to solve for, okay, the amount of thermal energy that's going to be released. So to do that, I'm just going to multiply both of these quantities. When you substitute them in here, 3.2 times 10 to the third, and times negative 36, and we end up with 1.2 times 10 to the fifth joules. Okay, and what we see there, okay, is right. There's a negative sign in here. And what this tells us is that energy has been released by the substance. In other words, the substance has lost energy, thermal energy, that is. Okay? So that's where that negative comes in. So then the next question asks, all right, okay, if you have a certain amount of this substance, and we know what the specific heat capacity is of lead, okay, how much do we have? Well, we can just take that, thermal capacity from the previous part, and we know, all right, that both equations apply from the previous page for thermal capacity and specific heat capacity. In other words, delta Q is the same, all right, but we have just two different equations of expressing that. Big C times delta T is equal to little m times C times delta T. And all I'm trying to show you guys here is that this is the relationship between thermal capacity and specific heat capacity, all right? We're just scaling up specific heat capacity by the amount of mass. So we're asked to solve for mass here, and the way we're going to do that is going to take big C and divide it by little c, all right, and that'll give us the mass. When we do this here, we have 1.2 times 10 to the fifth joules, all right, divided by 1.28 times 10 to the second joules per kilogram per Celsius, all right? And let's see here. Oh, I'm sorry, you know what? I took the wrong piece here. We want the 3.2 right here, there we go. Times 10 to the third. All right, there we go. And that's joules per Kelvin. And those units can cancel out, and they will give us kilograms, which turns out to be 25 kilograms. Spiffy. All right, so that is that problem worked out. Next here, we have another example. All right, so how much thermal energy is needed to raise the temperature of some sample of water from its freezing point to its boiling point? Well, given that we have here that you should be able to know is the freezing point and boiling point of water. You do need to know that information. Have the mass of the water here and the specific heat capacity of the water. We're just going to use our equation that the amount of thermal energy needed to do this is the mass times specific heat capacity times the change in temperature. And when you solve for this, you should end up with 1.05. Let me see how many sig figs do I have here. Yes, 1.0. Although with the temperature, that's right. That's just the defined thing. Yeah, 1.05 times 10 to the third joules. All right. So consider that. Okay, for the amount of thermal energy required to raise the temperature of liquid mercury to the same amount, And what it turns out is that you need less thermal energy for mercury since its specific heat capacity is lower. In other words, you add the same amount of thermal energy, you're going to get to a much higher temperature with mercury. All right? And what we see here, if we're looking at a temperature versus thermal energy graph, all right, in terms of the amount of thermal energy added versus the temperature that it changes to, what we get here, okay, are two different lines. One's for mercury, okay, and the other's for water here. If we actually look at the slope here, this delta T all over delta Q, this is equal to 1 all over m times c if we look at our MCAT equation, okay? And so mercury has that smaller c, which if it's in the denominator there is telling us the slope is going to be higher for it, okay? So the way I actually did this here is you can look at this equation right here, and if the mass is held constant, little c is going to be changing. All right? So that's that part right there. And the rest of the practice problems, I'll be happy to go over in class. So the next video you're going to watch will be on calorimetry.